Yeah. Hello everyone and welcome. Welcome back. I am 𝐒𝐮𝐩𝐲, a senior CPU design verification engineer currently working at Synopsys. I have been working in Synopsys for more than 1 year now, and before this I have worked at Intel Technologies for more than 2 years, and before that I have done my master's degree from IIT Kanpur, and there I have scored very good marks, very good grades, and I have been always passionate about VLSI, digital design, and verification domain. Okay, so in today's session, we'll be continuing our deep dive into the HDLBits question set solvings, and yeah, we'll be focusing on the next set of problems. Okay, and as always, pause the video, solve it yourselves first, give it an honest attempt, and yeah, after that, if you can't solve it or if you want to know my approach, let's look at the implementation details together. Okay, so yeah, let's start. Yeah, I'll be sharing my screen. I hope the screen is visible now. Okay, yeah. In the previous class, we have looked into the vector things, all the vector manipulation techniques, vector concatenation, replication, everything. Now we will look into modules hierarchy. By now you're familiar with a module, okay, which is a circuit that interacts with its outside through input and output ports. Okay, larger, more complex circuits are built by compressing bigger modules out of smaller modules and other pieces. Just give me a minute. So module is a circuit which interacts with its outside through input and outputs. Larger and more complex circuits are built by composing bigger modules out of smaller modules. Okay, and other pieces such as assign statements and always blocks connected together. This forms a hierarchy as modules can obtain instances of other modules. Okay, so it's like we can form a bigger module using multiple smaller modules. So we can instantiate multiple smaller modules inside a bigger module, connect them together, and basically many of the implementation details are masked in that case. So what happens is we implement something small in, let's say, a half adder, and we use two of those half adders to form a full adder, and then we use multiple of those full adders to form a ripple carry adder. So that is how we abstract layer by layer. Okay, so it says larger and more complex circuits are built by composing or adding together multiple, composing bigger modules out of multiple smaller modules and other pieces. So pardon me. So bigger modules are made with multiple smaller modules connected together and some other connections such as assign statements and always blocks. Okay, it forms a hierarchy as modules can contain instances of other modules. The figure below shows a very simple circuit with a submodule. Okay, in this exercise, create one instance of module A. This is the module A. Create one instance of module A here. Okay, and then connect the module's 3 pins, input and output, to your top level module's 3 ports. Top level, this is the top level module. and connect it to the ports of this input connected to A, input to B, output to out. Okay. Okay. The module A is provided to you. You must instantiate it. This is already present. We must instantiate it like this. Okay. When connecting modules, only the ports on the module are important. So while connecting multiple smaller modules to larger modules, only the ports of the modules are important, of the smaller modules. You do not need to know the code inside the module. You do not need to know the code inside the module. The code for module A looks like this. The code for module A looks like this. Module mod A, input in1, input in2, output out. Okay, end module. The hierarchy of modules is created by instantiating one module inside another. The hierarchy of modules is created by instantiating one module inside another, as long as all of the modules used belong to the same project. So the compiler knows where to find the module. The code for one module is not written inside another module's body. Code for different modules are not nested. So it's like the smaller modules are written somewhere else, not inside the bigger module. The code for the smaller modules are written somewhere else. We instantiate that module. We create a copy of that module inside the bigger module. Instantiation means we kind of call that module like a function. We call that module or we create an instance of that module as it is popularly called. And then we give the inputs to that module. We get the outputs from that module to here basically. We may connect signals to the module by port name or port position. For extra practice, try both the methods. So it says this connection can be done by name or by position. Okay, that is what they are saying. Try it. Okay. Okay. Connecting signals to module ports. There are two commonly used methods, by position and by name. That is what they are showing. Okay, so let's say module A, we are creating one instance and we are giving just the things, the names which is present in the top module, which should be connected to module A. This is called by position. Okay, this is called by name. So this is if it is written input 1, input 2 and input out, output out. So this WA goes to input in 1. Okay. This WB goes to input into and WC goes to output out. By default, this position is fixed. If I write WA here, that means WA goes to input 2 and not input 1. Okay. But here we can change the connections as we like. So I say WA is connected to input 1. I can write it here. I can write it here. I can write it here. I just have to write input 1 bracket in brackets WA. So I can write it anywhere. It means the same. Okay. This instantiates a module of type mod A and gives it an instance name of instance 1. Then connects signal WA outside the new module to the first port IN1 of the new module WB, to the second port IN2 and WC to the third port out. One drawback of this syntax is that if the module's ports list change, all the instantiations of the module will also need to be found and changed to match the new module. By name, connecting signals to a module's ports by name allows wires to remain correctly connected even if the port list changes. Okay. So even if I don't put in one WA here, I just put it here or I put it here, it doesn't matter because WA gets connected to IN1. That is fixed. Even if I put it anywhere. Okay. That position is fixed. Even if the port list changes, it's okay. This syntax is more verbose. However, the above line instantiates a okay. The above line instantiates a module named instance2, then connects wire 1 outside the module to the port named IN1, WB to the port named IN2, and WC to the port named out. Notice how the ordering of ports is irrelevant here because the connection will be made to the correct name regardless of its position in the submodule's port list. Also notice the period immediately preceding the port name in this syntax. Also notice the period immediately preceding the port name in this syntax. So it says dot in1 to in1 connect WA. Okay, this dot is very important. Dot in1 means in1 of this module in1. Okay. Okay. So we need to do the connection. What we will do is we will say module. Okay, not module. Basically the mod 1 module name is mod A, mod underscore A. Okay. Mod A, maybe MA, mod A, short form. It's anything maybe. And underscore A. And then what we can do is A, B, C we need to connect. We'll say A, comma, B, comma, C. Okay. This is what we need to do. IN1, IN2 out. Okay. 3 pins and A, B out. That is what we need to connect. Okay. That is what they have asked me to do. Okay. I think we are good to go. Oh, it was out. I didn't. It's a simple thing. Don't do it wrong. Okay. This is okay. We can also do dot in1 A dot in2 B and dot we have in1 in2 and out. So we can say dot out. Here also the name is out. Okay. There also the name is out. Okay. So let's see what is the solution. So it says success. Okay, great. So, okay, let's move on to the next one. Connecting ports by position. Okay. This problem is similar to the previous one. We are given a module named mod A, this one, and that has 2 outputs and 4 inputs. 2 outputs and 4 inputs in that order. You must connect the 6 ports by position to your top level modules ports out 1, out 2, A, B, C, D. So what we can do is, so this is given, copy it and the mod A, we don't need this module, it need mod A, m underscore A. I don't know why it came, okay, out 1, out 2. So we need to give out 1 to A, B, C, D. So it says here we have 2 outputs and 4 inputs. Okay, out 1, out 2, A, B, C, D. Now we cannot connect them by name because we don't know their names. Okay, input, 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 output, output. We don't know their names. We can connect 2 outputs and 4 inputs in that order. Okay, so yeah, basically that is what we can do. Out 1, out 2, and then A, B, C, D, and mod A. Okay, let's submit it. Success. Okay, great. They have given this circuit. They have given the inputs. Some inputs they have given, and what our circuit results output, and what the reference circuit results output. So those things are given. Okay. This problem is similar to module. You are given a module named mod A that has 2 outputs and 4 inputs in the same order. You must connect the 6 by name. Okay. The names are given. This is module A. And this is the top module. Okay. The right hand side. So we'll copy this. I'll just remove all these things. It is saying you must connect the 6 ports by name to top levels module ports. Okay. By name we have to connect because the positions can be different. Okay. Positions can be different. Out 1. To out 1 we will connect out 1. To out 2 we will connect out 2. That is what they said. And to in 1 we will connect A. To in 1 we will connect A. To in 2 we will connect B. To in 3 we will connect C. And to in 4 we will connect D. Okay. That is what they asked. Okay. We may or may not give a name. Here we did not give a name, but it's a success. Okay. Here we did not give a name. We can give a name under m_a or something. But yeah, that is what we need to do. Okay. We need to connect by name because the first two are output 1 and 2. That is not guaranteed. The first can be input 2, second can be output 1, third can be input 4, second can be input 1, after that output 2, then input 3. It can be connected in that way. I mean, the ordering we don't know. Okay. So yeah, we should connect by name. Okay. So let's go to this module shift. There are three modules. Okay. My DFF, D flip flop, D flip flop, D flip flop. Okay. You are given a module, my D flip flop, with two inputs and one output that implements a D flip flop. Instantiate three of them. So we have to instantiate all three of them and then chain them together to make a shift register of length 3. So we have to connect them one after the other and make a shift register. Shi- a register where value gets shifted. It can store 3 bits of length 3. The clock port needs to be connected to all instances. The clock port should be connected to all the instances. The module provided to you is module my D flip flop, module my D flip flop, and then we have input clock, input D, and output Q. Input clock, input D, and output Q. Note that to make the internal connections, you will need to declare some wires. Here, these two wire names need to be there. This is named D, this is named Q. This we have to name N1, N2, and this is basically clock which is connected. Okay. Be careful about naming your wires and module instances. The names must be unique. We cannot name this wire as M1 and say this is module M1. So these two names has to be different. Wires are N1, N2. Keep modules as M1, M2, M3, Mn. Keep it different. Okay. So what we can do is we'll say it looks like this. My flip flop. My D flip flop M1 module 1 will not say input and outputs. We'll say clock. After that we will say D and we will say N1. Okay, we will say wire N1, N2, wire N1, N2. If we don't say what is N1, it will by default consider it as wire. So we give D here, we give N1 here, we give N2 here. Okay. So we give N1 here, N1 is the input, N2 is the output, N2. And N2 is the input, Q is the output. N2 is the input, Q is the output. Okay. Okay. And here we will have M2 and M3. Okay. Yeah, basically it's done. So we give clock to all the clocks. We give D an output N1. We give this output N1. We give N1 as input and N2 as output. We give N2 as input and then Q as output. Okay. Okay, I think we are done. Yeah, success. Okay, I hope you understood this problem. It's a simple connection. We have the inputs and our solution and the reference solution, which are same. Okay, so let's move on to the next problem. Modules and vectors. Okay, so this exercise is an extension of the module shift. The last one. Okay, instead of module ports being only single pins, now we have modules with vectors as ports. This is the same thing, but this D is a vector, not a singular anymore. Okay, and all these are given to this multiplexer from where the output we are taking. To which we will attach the wire vectors instead of plain wires. Like everywhere else in Verilog, the vector length of the port does not have to match the wire connecting to it. Okay, but this will cause zero padding or truncation of the vector. This exercise does not use connections with mismatched vector lengths. Okay, you are given a module, my D flip-flop 8, with two inputs and one output, that implements a set of 8 D flip-flops. This means it's a set of 8 D flip-flops. Here we have only one clock. Here we have a D input, which is of 8 bits. And here we have a Q output, which is of 8 bits. Okay. It takes 8-bit input. So it's like, input 7 down to 0 D, output 7 down to 0 Q. Okay. Instantiate 3 of them and then chain them together to make 8-bit wide shift register of length 3. In addition, create a 4 to 1 multiplexer not provided. Also create a 4 to 1 multiplexer which is not provided, that chooses what to output depending on select. That chooses what to output depending on the select line. Here we will have a select line. Based on that, it will output either of these. The value at input D, after the first, after the second, or after the third D flip flop essentially selects how many cycles to delay the input from 0 to 3 clock cycles. The module provided to you is module my D flip flop 8. All these things I told you before. The multiplexer is not provided. We have to make it. One possible way to write one is inside an always block with a case statement inside. Okay. So what we will do here is, let's implement this 3 first. Okay. We will say my D flip flop 8 I can say M8A or M81. Okay. And then we'll say clock, and we have T, and we have output, and we will write here wire. Okay. 7 down to 0, N1, N2. Okay. The output is N1. Okay. So we have three N1, N2, and not Q basically. It is N3. Okay. This is N3, N1, N2, and N3. N3. This is N2. This is N1. This is D. Okay. D, N1, N2, N3. D, N1, N2, N3. Okay. And this is select lane. Assign y equal to q equal to q equal to select. So here we have select is 2 bits. So you can say select equal to 2 tick B11. Select equal to 2 tick B11. If yes, or 2 tick B00. Okay. If select equal to 2 tick B00. Okay. Then output D, D. Otherwise, if select equal to 2 tick B01. Okay. 01. 10. If that's the case, we give as N1. Otherwise, we give as N2. Otherwise, we give the output N3. Otherwise, we give 8 tick BX. So what we do is we say if select equal to this, assign D to Q. Otherwise, assign N1 to Q. Otherwise, assign N2 to Q. Otherwise, assign N3 to Q if select is 3. Otherwise, assign X, 8 tick BX to Q. Okay. So this solves our thing. Okay. It's a cascaded kind of, you know, ternary operator. Let me see what they asked to do. Okay. Yeah. So status is a success. So I hope you understood this. I'll tell you. We have to define 3 wires. So This doesn't have a name. This is D. This we named as N1, N2, and then N3. This N3 goes to 3 of this multiplexer. This N2 goes into 2, N1 goes to 1, and D goes to the 0th position of 0th input of this multiplexer. These are the inputs. Okay. Third input, second input, first input, and 0th input. And here we give the select line. Here we give the select line. And we check if the select line is 0, then Q equal to D. If the select line is 0, okay, select line is 0, then this is D, which is connected to Q. Q equal to D. Okay. Q equal to D. Otherwise, if select line is 1, so it's like if select line is 0, do D, the output is D. Otherwise, this. So first we check, then if select is 1, then output is N1. If select is 1, then the output is this N1. Okay. Otherwise, if the select line is 2, the output is N2. Or if the select line is 3, the output is N3. And the output Q becomes equal to like that corresponding value. Okay. So we have submitted, we got success. Okay, great. It's a good start. We have learned a lot of things here. We have learned about modules and vectors. Okay, so we will start with adders and all in the next class, in the next session. Okay, so yeah, that completes this problem. And yeah, uh, if you have approached any of these problems in a different way, or if you have a better solution, please do let me know in the comments. Please let me know your solutions. And if you have a better way, please do post it in the comments. If you have any doubts, ask it in the comment section. I'll answer it. If it's a long problem or long thing, a big thing that I need to describe or something, I'll create a separate video on it. Okay. And I'm always interested in discussing the various implementation styles of these problems. And okay, if you have any doubt, let me know. If you have any comments or feedback, please do let me know in the comment section. Please do like, share, and subscribe this YouTube channel. And thank you for attending. And we will meet you in the next class with the next set of problems. Thank you. Bye.